Okay, here we are in week 5, lab 5. This is William Schwab. And this week, we're going to look at DC motors and robotics. And here's the first objective. And this is just trying pulse width modulation on an LED. Now over here, we go over here, here's the program. Now it's pretty simple. We have just a duty cycle that we're putting in, and we're putting in numbers. 64 will be 25%, 128 will be 50, and 192 is 75%. Now I do not have a digital scope as I'm recording this, so what we're doing is we are running a serial monitor. We can look at it. Right now we're loading up 64 duty cycle, and what we can see from the serial monitor is we've got like 1.25 volts, which is good. That's 1/4 voltage. Now when we look at our LED, that's our LED. Now I'm going to go back here and we'll see. I'm going to change it to 128. And we'll load that one. And it's kind of hard to tell because light goes out and then it goes back on, whether it's brighter or not. And if we go back over to our serial monitor though, we can see that we're at 2.5 volts. And we'll do the same thing with 192. Now the one thing when I was doing this that I found out is I started out, I'm putting out the voltage and printing it on the serial monitor, and the serial monitor is a great thing. But the one thing I noticed was I started out with the duty cycle being an integer and then multiplying the voltage as a float value. But if you have one as a float and the other as an integer, it's going to assume the integer value, not the float value. So originally when I was looking at the serial monitor, I was always getting numbers like 1 volt, 2 volts, and that type of thing. I wasn't getting it. Like here it's 3.76, that would have came out 3 volts, it would have been truncated. And here is the LED. I guess it looks a little bit brighter, it's hard to tell. So that's kind of an important point, is that if you want something to have a float value, everything that multiplies, it better be float also. That's objective 1. Okay, now here's objective 2. Now we're just going to the DC motor, and we're saying what voltage or what current flows in the motor when we get that. So I've got my little meter, and what we have here is we're going from our battery terminal out to the red lead, coming back from the red lead. Now I have it going through a switch just because I don't have enough hands to do everything. So we have it going through the switch to our motor. We've got our motor velcroed down so we don't keep breaking off its leads. And when we press this, as we can see, our motor does start moving around. And you can, if you can't see it, you can tell it by the way it you can see it torquing on the velcro strap a little bit. And we can tell it is because we'll go and look at our meter here. And when it's running, we get about 100 milliamps. Okay, now, and this part's going to be difficult, but I'm going to grab. Oh, and another thing is when we first turn it on, you can see that it jumps up to like 1/4 amp. And it varies because it's kind of not real time. Now I'm going to hold on to the thing, the shaft, and now we get like 1.82 amps. And so I guess we have to do this because I don't know, all employers are clamoring for everybody who can make this measurement. I'm glad we didn't have to start a fire, otherwise I'm sure we'd be videotaping us rubbing 2 sticks together to get the fire started. But that's objective number 2. This is also as part of objective number 2. We are supposed to look at the maximum output from each pin. And so I went to the Arduino site and I got about, I don't know, about 10 different people had about 13 different answers. So I decided to go to the actual microcontroller data sheet. And here you can see that it's pretty clear the maximum, absolute maximum per I/O pin is 40 mils. And for the whole chip it's 200 mils. So you certainly can't be running a whole bunch of them at 40 mils. But anyway, obviously our output pins cannot drive the motor since the motor is running at about 100 mils. So we have to drive it either directly from the battery, which we were doing there, or what we're going to do now is we're going to drive it from a FET. And we'll see how that works. Okay, for the third and final objective, we're going to try to run the DC motor through a pot, and it'll be controlled with the pulse width modulator through not the transistor shown, but a FET, which actually the FET is actually cooler and takes 33 amps it can output. So we can drive a considerable package, not just our little 100 mil motor. And so what we've got over here is we've got a pot, and I put kind of something that you can see that the motor does rotate a little bit. And right now, if we look at that, that's about quarter amp, or a quarter volt, that what we have on the motor. So it starts running at a quarter volt. And if we go over here and we adjust it, we can, like there, we're about 0.37. There we just went down and we stopped the motor, but we can see what happens when we start getting it going. That's about 0.4 of an amp. And it's hard to tell what the speed is actually, but that's even at 1 volt. Probably the best indication of how fast it's going is the sound, so we'll just listen to it for a second. 2 volts, 3 volts, 4, and that's full out, 5 volts. And it flipped our cap off so we can no longer get an indication of what it's doing. But that's the third objective. And with no cap, it still starts running there. It just starts barely moving at about 0.2 of a volt. So the cap apparently didn't weigh it down that much. Alright, that's Lab 5.